last couple of lectures, we have reviewed the basic concepts that is required to analyze the problems with rotational motion of extended objects or rigid bodies. So, now it is time to consider some practical situations. So, today we are going to talk about situations which involves both translation and rotational motion. So, these things situations are usually kind of confusing sometimes, like the motion can become really complicated. So, we shall confine ourselves to not the most general kind of motion, but a special case in which the what is called the plane motion of rigid body. What does it mean? It means we will consider this special case where the direction of angular velocity is constant or fixed. That is, the angular velocity can change in magnitude, but its direction will not change. So, we are going to assume this is the scenario. This basically means that our in the rotational part of the motion, the axis of rotation is not changing itself with time. So, now in order to our goal is to develop a systematic strategy to analyze combination of translation and rotation. So, we are going to talk about some computing rules for different quantities one by one. So, our basic strategy is the following. So, suppose this is an object which is undergoing a combination of plane motion, that is a combination of translation and rotation. So, what we are going to do is that we are going to divide the motion into two parts. So, let us say this is our system. So, this is our system and we are going to divide the motion into two parts. So, let us say that our first goal is to answer this question, how to describe the velocity of such an object. So, the first part, so we are going to put a pivot point inside the object. So, let us say this point is A. So, this is our pivot point on the object. The natural choice of this point, as we shall see, is the center of mass of the object, but we will also take example that we do not have to take center of mass, it can be any point in the object. Then it is always possible to describe, let us say, any other point B, the motion of B with respect to our lap frame or a frame, inertial frame with fixed origin, in which this, so this is the frame in which we are observing this motion of this object and the object is doing some combination of translation and rotation. So, it is always possible to break the motion of any other point B as a translation of the point A plus rotation about the point A. So, a translation of the point A and a rotation of the point B about A. So, this is going to be our strategy. Then the velocity of this point B will be the velocity of the point A due to its translation plus the relative velocity, which is denoted by this B slash A notation. So, relative velocity of B with respect to A. So, we have two pieces. So, we have divided the velocity of the point B, which is this velocity B with respect to the lap frame in which the motion is complicated. Then we are divided into two parts, two simple parts. One is that the reference point A, translation of the reference point A, which is supposed to be simple to understand, and then the rotation. So, if you put A as a center of a circle and then take the distance A to B as a radius, and then this is doing a rotation, a fixed axis rotation about the point A. So, the B is moving in a circle with a about A with a. So, this is the second piece of the. So, this is also something simple. So, motion in a straight line or translation of a point and rotation about the point. Now, the For the case in which we are considering that the axis is it is a fixed axis rotation, the axis of rotation is fixed, in that case the translation of the rotation part, the velocity of the point B, the rotation of B about A is given by simply the angular velocity times. So, this is the definition of from definition of angular velocity. So, angular velocity of the object which is same. So, the angular velocity of a rigid body in plane motion is independent of reference point. If the body is rigid, then all you can sort of look at like it is a kind of from experience we know, if it is a rigid body and if it is rotating, then all the point must have the same angular velocity, otherwise the body cannot be rigid. So, this part is same and this is independent of the reference point, and this part denotes the location of the point B with respect to A. So, if we take the magnitude, and this is a cross product of the magnitude of, so note that I have put it a note the notation. So, the bold's face means a vector and without bold means scalar. So, this is the magnitude and this is the full vector. The crucial point is that this reference point A can be arbitrary. So, this we shall see. So, this is our choice, and so we shall we try to choose a point which makes the problem really simple. Okay, so this is our strategy, and we can do the same thing with the acceleration. So, again we are considering for simplicity a situation in which the axis of rotation is fixed. So, this is a plane motion. So, the direction of omega angular velocity is not changing. In that case again, so this body, the object can move with an acceleration. So, it does not need to move only with a constant velocity, it can have acceleration. There could be for example, if we talk about a sphere rolling down a plane, it is definitely accelerating. So, in that case again we choose a reference point A which can be arbitrary, and then our strategy will be that this motion is a translation of the point A and the rotation about A. Now, in this case the acceleration, so this is the rule for computing the acceleration of the point B. Again, so AB is the desired acceleration that we want to compute with respect to the lap frame. The acceleration due to translation of the reference point A plus the acceleration of the point B due to rotation of the point B about reference point A. So, note that the even though the direction of the magnitude, the direction of the angular velocity is not changing, but this magnitude can change, hence there could be acceleration of the point B with respect to A. So, I just mentioned that the expression for this relative acceleration of the point B with respect to A, it has two pieces. The one piece which is directed along, so this is so kind of you consider a circular motion of, so this is point A, this is point B, this is the location of the point B with respect to A. Now, if this moves in a circle, as you know that its direction is continuously changing, so it must feel a acceleration towards the center of the circle, that is towards A, which is this term, that is the centripetal acceleration. But if the magnitude is also changing with of the particle is also changing, then it can also have in general an acceleration in the tangential direction as well, and this is coming from this term. So, here this alpha is the angular acceleration. So, the omega, so alpha is equal to the rate of change of omega, that is this is d omega dt, and these are the different pieces. So, these are the two pieces in general. So, this is easy to prove in spherical using polar coordinates in 2D polar coordinates, but here I just state them without proof. Next, angular momentum. Now, this is again a strategy, the same strategy we are going to use, that we will take so see this object is moving and its angular momentum will have again two pieces. We want to compute the angular momentum in the laboratory frame, the lab frame. Now, in this case, for a very general setting, it is true not only for the case where the angular velocity is direction of angular velocity is fixed, but also in a case where the direction of angular velocity can also change. But in most generally, there is a theorem which is called the Chasles theorem, which says that the angular momentum relative to the origin in our lab frame, in which is an inertial frame in which Newton's second law of motion is valid, Newton's first law of motion is valid, and in which is a fixed origin frame. So, and we want to compute the angular momentum of the object in that frame. So, that has again two pieces. So, look at the center of mass. So, now we are specializing to center of mass frame, because we shall see in many different cases, out of all the possible reference points, center of mass is often the simplest choice of the reference point. So, treat the body like a point mass located at the center of mass, and then that may have some motion, maybe translational motion, that can generate some angular momentum about our origin of the lab frame, plus the angular momentum of the body relative to the center of mass. Again the same strategy, we are dividing this complicated motion into two simple pieces. The first thing is that think of a point, the whole or extended object is like a point mass concentrated at the center of mass, and this is moving translation of that point, plus the rotation about the center of mass, which generates some angular momentum relative to the center of mass. So, in equation, so the angular momentum in the lab frame will have these two pieces. So, the first piece, so let us say this is our origin in the lab frame, and this is some point inside the body, some let us say consider for example a point mass, some point inside the body, and which is in the lab frame. This motion of this point is complicated, it has some translation and some rotation. So, what we are going to do is that this is the center of mass of the object, and the location of the center of mass is r in our lab frame, and location of the point is small r in the lab frame. Then the motion of this point, the angular momentum of this point is the angular momentum of this point about the center of mass. So, if we put center of mass as our pivot point, calculate the angular momentum, which is LCM, and plus this, if the center of mass itself has some velocity, then it will generate some angular momentum given by this expression m r cross b or r cross p, where p is the center of mass momentum. So, just to denote the symbols, so m represents, capital M represents the total mass of the object, capital R is the center of mass position, and capital V, note that m is a without bold, but so this is a scalar, not bold. R and V are vector, so they are marked, denoted in boldface. And the center of mass, if omega prime is the angular velocity about center of mass, then we learn that the angular momentum is the I cos omega, where I is the moment of inertia. If it is a fixed axis rotation, simple rotation about a circle about the center of mass, then our I cross omega is simply has only so the omega and L will be in the same direction in this particular case, and in that case we can simply calculate the moment of inertia component along the appropriate component times the angular velocity. Okay. After center of mass, so far we have not talked about energy, but if there is a rotational motion, it also generates some velocity. So, it also generates some sort of kinetic energy. So, we should, in order to analyze the problems, we need some expression to calculate the kinetic energy due to rotation. Again, we use the same strategy. So, our theorem says that the kinetic energy of the object will be such that it has as if that it will have two pieces, as if the whole object as a point mass located at the center of mass location plus the kinetic energy due to rotation, pure rotation about the center of mass, pure rotation about the center of mass. So, this is the two pieces. The first piece denote the motion of the center of mass, a point mass with mass capital M with velocity capital V located at the center of mass. So, this will have kinetic energy half mv square, and second part is the kinetic energy of the rotation due to the center of mass. So, let us see how the second part comes in. So, here, so we start. So, in this case I am using capital T to denote kinetic energy. So, note that kinetic energy is a scalar. So, the T is without boldface, but velocity is a vector. So, it is with boldface. So, now we know that suppose this point has some velocity v, which is a combination of the total velocities in the lap frame. So, it is a combination of all the complicated motion resulted in a velocity v of this point. Let us say this is a small mass element dm. Then its kinetic energy is always half m v square, that is half v square times its mass dm. Now, this v has two pieces. So, the first piece, so this is the v, the first piece come. So, r from this picture is r plus r prime. So, if I take all the derivative in the lap frame will be so this is our v, and this is capital V, which is the velocity at the center of mass, and this is v prime, which is the velocity of the point with respect to center of mass. So, then our v is in capital V plus v prime square, and then if you expand this square, then you end up with, do the algebra, you end up with this expression that this kinetic energy of the object in the lap frame has two pieces. First piece is due to the as if the whole mass is concentrated, whole object mass is concentrated at the center of mass and is moving with the velocity of the center of mass, and the second piece is turns out to be of the form the moment of inertia times omega square. So, this is the expression for kinetic energy due to rotation. So, this piece is the kinetic due to rotation about center of mass, and you can also, using L equal to I omega, you can also write this as in this particular form omega times L. So, dot product between the vectors omega prime, which is the angular velocity in the center of mass frame, dot the dot product and the angular momentum in the center of mass frame. So, the other notations are explained already. So, let us now apply these rules to systematically to solve problems, because our goal is always to sort of develop a method to solve problems. So, let us look at this problem. So, our first problem is the following. So, we have a rolling gear. So, this is a picture of a gear. It's so it's a double gear. So, 1 and 2. So, gray and blue, two gears, and they are moving in such a way that the, so there is a rack on the lower side which is at rest. Now, this gear mechanism works in such a way that the center of the gear A is moving to the right with some velocity V A, which is given by 1.2 meter per second. So, now the size, that is the radius of the smaller gear is given, which is R2, which is 0.1 meter, 100 millimeter, and the bigger gear is R1, which is 150 millimeter, that is 0.15 meter. So, the question is that what is the if this center is moving with linear velocity 1.2 meter per second, then what is the angular velocity of the gear, and it put two different reference point. So, because of this gear is moving the rack on the top is also moving to the right. So, this is the mechanism is doing. So, the rack at the bottom is fixed, the rack at the top is moving. So, what is the velocity of the upper rack R and another point D on the gear, what is their velocity? So, how to solve this problem? Again our strategy is the following. So, we simplify this picture like a two concentric circle. Then this is our system. So, this is our system, and now in rotation, after specifying the system, we also need to specify the reference frame, what is the lap frame. So, let us say a lap frame is a fixed origin frame in which this whole thing is moving. So, we are going to describe the complicated motion of this gear as the translation. So, we will take this center point A as our reference point. So, this reference point is moving with some velocity V A. So, this is the translation piece, and every point on this gear is rotating about A. So, that is going to be our rotation piece. So, if we combine these two pieces, we get the full motion of any point on the gear with respect to the lap frame. So, this is our so called rolling motion of a wheel. So, this is our strategy. Now, let us calculate the numbers. So, the first thing is that if the gear, so first thing to note that we are going to assume this condition that this is a pure rolling without slipping. That means that the point of contact, the instantaneous point of contact of the gear wheel with this lower rack must be 0, because it is given that this lower rack is not moving. So, that means the point of contact of C must be 0. Then we can see that this basically give a constraint that the V A, so V C has two pieces, one is V A and plus the motion of the point C with respect to A, which is omega cross R C A, and that is 0. That means the magnitude of V A must be equal to magnitude of omega cross R C A, that is the location of. So, this is our R C A, that is the location of C with respect to A. So, this is simply omega. So, the omega is clear from this picture if you apply right hand thumb rule, that let us say this is our x axis. So, let us say this is our x axis, this is our y axis, then the omega must be in the some z direction, because since this gear is going right side, that means the omega must be into the plane. So, it is given that V A is equal to 1.2 meter per second and R C by A is the radius of the bigger wheel, which is 0.15 meter. That means omega is 1.2 meter per second divided by 0.15 meter, which is equal to 8 radian per second. So, this is the velocity of the point omega. So, what else? So, now we want to find out the velocity of the upper rack R and the point D of the gear. So, the upper rack R has the same velocity as the point of contact between this smaller gear and the upper rack. So, V B is going to be V A plus V the relative velocity. So, just to clarify, so this is the magnitude of the velocity. So, in the vector notation, the angular velocity vector will be in z direction. So, this minus sign is denoting that this is in the going into the plane. so the relative velocity of this point B with respect to A. So, then this is equal to V A plus omega cross R B, the location of B with respect to A, which is, so omega is minus 8 radian per second z hat cross. So, the B is along y axis. So, this would be R 2 times y axis y hat, and this is 1.2 meter per second x hat. So, this is 1.2 meter per second x hat plus, so z cross y is minus x and this is minus, so this is x hat. So, this vector is clear from the picture that this the rotational part. So, the VBA is along the positive x direction. So, in the same direction as the VA. So, this will be 8 times 0.1. So, 8 meter per second into x hat. So, this is 2 meter per second x hat. Now, what about VD? So, VD will be VA plus VD, the rotational, the velocity of the point D due to the rotation, which is omega cross R dA, which is 1.2 meter per second x hat plus minus 8 radian per second z hat cos. So, this is, so this must be going in the upward direction. So, this is minus 0.15 meter x hat. So, this is 1.2 meter per second x hat plus 1.2 meter per second y hat. So, you can see that the net velocity in the lap frame of point D will be this direction. It will have two components. This component, horizontal component, is due to the translational motion of the point A, and this component is due to the rotational motion of about the point A. So, to summarize, today we did sort of looked at a situation where there is a combination of translation and rotation, and we learned how to systematically approach those kind of problems. We shall going to take more example in the next lecture. Thank you.